In the last two lessons, we discussed harmonic waves. In today's lesson, we will discuss a special type of harmonic waves called harmonic sound waves. Well, what are sound waves? How is sound produced? Well, sound is produced by any vibrating object. You can see sound is produced by any vibrating object. If I have my aluminum pointer hit something, you can see it produces sound. So sound is produced by vibrating object. When an object vibrates, it sets air particles into vibration, and that vibration is handed over from particle to particle so that the energy of vibration travels from one place to another. When I am talking, what is vibrating is my voice cord. My voice cord sets air particles into vibration. What type of vibration? What type of wave is sound waves? It is actually a type of longitudinal wave. Now look at this object. This is called a tuning fork. If I hit this, I set this into vibration, and listen to this. You are hearing the sound of vibration of this tuning fork. So actually, sound is a form of energy. Is that right? Sound is a form of energy transfer which needs a material medium to propagate through. If there is no air between the camera and me, you will not be able to hear me. Sound travels through a medium. Now, when I speak, I set the air particles into vibration, and that vibration eventually reaches the camera, which then records the same vibrations. Sound is propagated through solids, liquids, and gases in the form of longitudinal waves. What are longitudinal waves? In a longitudinal wave, the particles vibrate back and forth. The wave advances in the same direction. When I say the same direction, remember, it doesn't mean if the particle vibrates backward, the wave will move backward. Well, if the particle vibrates back and forth, a wave moves to the right as well as the wave moves to the left. So the particle vibration and the direction of propagation of the wave are basically the same. In a longitudinal wave, the direction of particle vibration is the same as the direction of propagation of the wave. Of course, we already said sound is produced by vibrating object. Now here I have shown something similar to the tuning fork. Now a vibrating object has an equilibrium position and two extreme positions. Now, if the vibrating object is at the left extreme, as it moves to the right, it will push the particles of the medium together, forming a region of high density. You remember longitudinal waves have regions of high density and regions of low density. Regions of high density are called compressions, and regions of low density are called rarefactions. Well, how are these formed? As the vibrating particle or the vibrating object moves from left extreme to the right extreme, it pushes the particles forward, and that is where you have a region of compression. When the vibrating strip moves back to the left, it creates a space. That means the particles will vibrate back, and that is a region of rarefaction. So, take note of this. If a particle is vibrating forward, A particle vibrating forward is in a region of compression, and a particle vibrating backward is in a region of rarefaction. Remember, the vibration of a particle has two parts. It vibrates forward and then backward. During the forward vibration, the particle is in a region of high density. During the backward vibration, it is in a region of low density. As the vibrating object moves from extreme left to the extreme right, the particles of the medium are pushed to right, and a region of high density called compression is created. And this region of high density is propagated to the right. Now, in the same way as the vibrating object moves from right to left, the particles of the medium are pulled back, creating a region of low density called rarefaction. And these compressions and rarefactions advance through the medium, and when it reaches your eardrum, that compressions and rarefactions apply varying pressure on your eardrum, making your eardrum vibrate exactly the same way the object is vibrating. That means you hear that sound. The particles of the medium are thus set into simple harmonic vibrations. The air particles are set into simple harmonic vibrations. That means sound waves are harmonic waves. Now, when the particles vibrate in the direction of the wave, they are in a region of compression, I told you that. And when the particles vibrate in a direction opposite to the direction of propagation, they are in a region of rarefaction. Now, let me see if I can illustrate that on the diagram here. So, if a particle is in a region of compression, look at that, the particle here will be vibrating to the right. And when it is in a region of rarefaction, it will be vibrating in the opposite direction. So, a particle in a region of compression, it's vibrating to the right. A particle in a region of rarefaction is vibrating to the left. Okay. The compression and rarefaction in a longitudinal wave is actually analogous to the crest and trough of a transverse wave. Now, if you notice, it is much easier for us to draw the crest and trough of a transverse wave than to draw the compressions and rarefactions. So even where we want to draw a sound wave, we will use the transverse wave form, the crest and the trough. But remember, when you draw a crest, it means a compression. When you draw a trough, it means it is a rarefaction. There you are. So I have drawn now a transverse wave form. The crest of the transverse wave corresponds to the compression of the longitudinal wave, and the trough of the transverse wave corresponds to the rarefaction of the sound wave. Okay. The vibrations of particles at the center of a compression differ in phase by pi with those at the center of a rarefaction. You understand that, don't you? Because at the center of a compression, if the particle is moving to the right, at the center of a rarefaction, the particle is moving to the left. So their state of motion, or they are completely out of phase, or the phase difference is pi. The phase difference between a particle at the center of a compression and a particle at the center of a rarefaction is pi. Just the same way, as the phase difference between a particle on a crest and a particle on a trough is pi. The wavelength of a longitudinal wave. Can you tell me what is the wavelength of a longitudinal wave? Now, what is the fundamental definition of wavelength? The fundamental definition of wavelength is the distance between two nearest particles in the same phase of vibration. If you watch here, at the center of a compression, the particle is moving to the right. So to find a particle that is in the same phase, you've got to go to the center of the next compression. So the distance between the centers of compression or the distance between the centers of rarefaction is a wavelength. So wavelength is the distance between the center of a compression and the center of the other compression. My arrows actually haven't come very well. I should have put the arrow like this. I actually put it at the right place, but it got shifted. Now, this is a wavelength. A distance measured from the center of one compression to the center of the other compression is a wavelength. All right. I have shown you this illustration before. You have a vibrating object. You can see this red object is vibrating back and forth. And you can see as it vibrates to the right, it creates a region of high density, and that region of high density moves away. As it moves to the left, it creates a region of rarefaction, and the rarefaction also moves away. But if you look at an individual particle, now look at any of these particles. I'm pointing on one particle. Look at the way it is vibrating. It is simply vibrating back and forth. There you are. So the particles vibrates back and forth. The particles are not moving away from their positions. That is an important characteristic of wave motion. Now, when the particles vibrate to the right, they are in a region of compression, and when the particles vibrate to the left, they are in a region of rarefaction. All right, so this, you have actually seen this before, but I showed this to you one more time to reinforce the concept of longitudinal wave. Let's now talk about the speed of sound waves. How fast does